He will talk about automated text coding.
Thanks for having me. Thanks for the invitation, Seth. Wow, that is bright. Okay. Wouldn't it be great if you could just get the machines to do all the work? I'm sure that's why some of you are here. You would prefer not to have to read. So there's good news and bad news. Machines can do some of the work, but you also have to do some of the work yourself. And I really specialize in this idea of teaching people how to train humans and machines to do work together and to do it better. And the problem is, in a nutshell, that categories are soft and some are softer than others. And the problem of putting text into categories is frustrating, particularly if you ask for people to put 100 items into 3 categories and they don't all agree, and then you ask them a week later to do the same thing and they don't agree with themselves. So what does that tell us? It tells us that the problem is not a simple one, and that we need to work on a variety of techniques to get to where we need to be. Now, my background is not in machine learning or computer science. I'm a political scientist and a historian. This was the data from my dissertation some time ago, crumbly old newspapers that used to come wrapped in butcher paper, and that I went through, old school, the way that people do, looking for bits and pieces of text that correspond with ideas or concepts or themes or topics. And in fact, one of the things that I'm a big fan of is just the inductive method, data-driven method of developing the categories relevant to your study out of the data rather than deductively, but I'm a pluralist, so I support going both ways. We started using software in 1999 to sort public comments on proposed federal regulations. Actually, most of my customers are my biggest customers are U.S. federal agencies, and they sort comments on polar bears and gray wolves and whether pilots should have guns on airplanes and whether or not we should let people get visas to come into the country in this day and age. And we used to use a program called Nudist, and the big problem for me was a lot of clicking and dragging and pain in the elbow and things like that. But we also learned that it was difficult to do this work for reasons that are probably familiar to anybody who has done the work themselves, which is it takes time, it costs money, it's hard to manage, people are unreliable, the models are wrong. You have to really start with this. This is a great article, by the way, the Grimmer and Stewart, because it summarizes more than a decade of experience that I have running teams of human annotators, coders, text labelers. And the big takeaway here from this article and from this talk is that no matter what method you use, whether it's a human method or a machine method, or ideally a mix of both, that you should always have steps for validation. And one of the big mistakes that people make is thinking that there's a machine or a human out there that can put words into categories without validation of any kind. There isn't, and there aren't. And so you shouldn't. And when we started building software, it was in, and I'm sorry, PDF kind of washes things out here, but it's free, open source software. You can find it on the web. It was hosted at the University of Pittsburgh for years, and allows people to work in groups to label data and to do certain measurements around that data. Hopefully this will be readable. There we go. So what kinds of things are we interested in? We're interested in whether people will agree about the proper classification for a chunk of text. And when they don't agree, what are we going to do about it? We call that process adjudication. And the adjudication or validation of human observations is one of the critical pillars of what we've done as researchers and as a software company, which is to try and build a system for people who need to get this work done quickly, but also would like to get it done accurately and would like to be able to report some measurements on the accuracy of the humans or machines that are doing the work. And so one of the first things that we did was to develop a workflow, web-based. You work through a browser where items load to the screen, and you simply hit a keystroke, a 1, a 2, a 1, a 3, a 1, a 4, whatever the coding scheme might be. But we wanted to take the mouse out of the picture and to speed up the process of recording human observations. And we do that basically by having items load and people code. It loads and codes, it loads and codes. And this is what our keystroke coding looks like at this current date. This is actually a tweet being coded. There's some labels. They're associated with numbers 1, 2, 3, 5. The owner of the data set does this. And the process of distributing this labeling out over the web to groups is something very similar to what people do with Mechanical Turk. If you have any computer science friends, they'll know what that is. And speaking of computer science, the background for this work, really, and for some of the breakthroughs that we made in this work, came from 10 years and about $4 million of National Science Foundation funding in collaboration with leaders from the field of information retrieval, natural language processing, statistics, sociology, education, and other fields. We were all working together to better understand the problem of how to do this labeling and how to do the measurements around the labeling. And NSF's dictum, really the dictum of every computer scientist I've ever met, is measure everything. And so we do. We measure things like how fast is an individual annotator compared to the others. It turns out there's quite a significant variation across human annotators. Some are slow, some are fast. Sometimes that slowness is a good thing if you want people to be careful and to make reflective observations. Sometimes we're just looking for people who can get the job done as quickly as possible. Another critical measurement for us is that one I started with, where if you give a group of people a set of items and ask them to label, will they agree? In this case, we were labeling Chinese microblog data from Tencent Weibo. The keyword we used to pull the data was Malaysia. It was around the time of the shoot down of an airplane. We were simply asking the human observers, is this or is this not about the shoot down of an airplane? And in this case, we have a very high score, sort of unbelievably high score, because the task is fairly simple. It's a relevance task. Is the item relevant or not to something we care about? And because it's a relevance task as opposed to a topic or as opposed to a sentiment or emotion, there's usually a fairly clear-cut answer with some borderline cases. A big part of what we focus on is how you bring those borderline cases to the surface and identify the boundaries of your coding categories. What is a borderline case? Why is it a borderline case? And why is it causing human annotators to disagree? Now, the other thing that I would say that is unique about our approach, probably the most unique thing about our approach, is when annotators do disagree, what do you do about it? In this case, we've got at the bottom, one of those Tencent Weibo posts and the metadata above it. And what I'm doing in the adjudication module is just looking at how the 5 annotators have labeled this one piece of text. 4 of them agree it's about MH17, and 1 of them thinks it isn't. Now the thing here is you don't even need to speak Chinese to know that that one coder has made a mistake. Right? This coder, the first 4 characters of the tweet are MH17. It's clearly, there's a 777, 370s in their plane that was shot down. It's a clear error in a simple task. And the reason I show this to everybody is, one, this process, this mechanization of adjudication is very important because it allows you to do certain things like get rid of all the bad observations, the false positives, learn something about the coders, create a gold standard training set, but also feed back to the annotators information about what is a good observation and what is a bad observation. So this is a very important step. And I would go further and say, if we just look, I don't know if there's a pointer on this. Yeah. I don't know if you can see it. In that example on the left, coder 2279 is the one who just made that mistake. Turns out this coder was only right about 61% of the time for over 200 items for a task that other annotators could do at the rate of 97 or 98% accuracy. Now that's an extreme example. Actually, there's 2 coders there who are doing a very bad job at labeling text that is very easy to label. And what we've learned from doing this kind of multi-coder measurement adjudication over a period of now greater than 15 years, really, is that for every task, there is a distribution of human aptitude that is out there. And you can't assume that the 2 people that you've selected to label your text are going to label it correctly. They're entirely idiosyncratic. it's much better to assume that there's going to be a distribution of competencies across your annotators, ranging from very poor to very good, and there'll be very few who are very poor, and there'll be very few who are very good, and there'll be the great middle who are average. And that great middle who are average are only going to put words in the right categories about 3 out of 4 times, which means a quarter of all their observations are going to be invalid. This is a really important point. Good human annotators are hard to find. When you do find them, you don't want to let them go. Now, in terms of CoderRank, it was March 1st when we were awarded a patent for CoderRank, and I just want to say that, this is my big idea, and I don't know if I'm ever going to have another idea like this again, but the basic idea is that there is this sort of universal law, and that universal law is, for a particular task, some people will be good at it, and some people will not be good at it. And it is best when training machines to weight more heavily the people who are good at it. And so to the extent that we track, measure, monitor the likelihood that humans are going to make valid observations, and then we want to go to machine learning, it is very important to weight more heavily and to use more heavily the humans who are most likely to create valid observations, because if you use Coder 2279 to do all your coding, your machine learning is never going to work. So just quickly, how do we do machine learning? We use a combination, what I call the 5 pillars. They work together nicely. They can be used independently. One way to accelerate machine learning is just by using simple search techniques. If you know that there are things that are highly relevant to a topic you care about, you can use search to put them all in a bucket and then train off that bucket. And you can train on hundreds or even thousands of items at a time. We use filtering as a way of pulling out certain types of items that may have metadata associated. So survey data has all sorts of interesting metadata if you're working with the open ends, but we do a lot of work with social data, with email data, with public comment data, and the filtering there is quite important. One of our key technologies we developed for the federal government is duplicate detection and near duplicate clustering. The main idea there is, and this works very well with surveys as well, and it's a true accelerant to machine learning, is that across any collection of unstructured text where people are freely writing it, or this is Chinese tweets, but lots of retweets in them. But if you had a survey with 5,000, 10,000 respondents, a lot of people are going to write the same thing to certain questions. And if you want to train a machine to find the no answers, or to find the unhappy people, or to find the people who are talking about a particular topic, first running all your data through duplicate detection and near duplicate clustering is a very good way of creating a purposive sample that can accelerate the process of creating an effective machine classifier. Fourth pillar for us is the human coding. That's where we started all this work and where most of our IP and energy goes, getting people to put things into the right categories, and then ultimately machine learning based on adjudicated, gold standard, high quality training sets. The techniques that we've developed were designed originally to make computer scientists happy. And the thing that makes a computer scientist most happy is to hand them a high quality training set. And what we've tried to do is to lower the barriers or the bars to the creation of those high quality, gold standard training sets. And that's what we mean by humans and machines learning together. Is if your humans aren't able to do the labeling, the machines won't be either. But if you can demonstrate that the humans can create a consistent, valid, gold standard training set, then you can build a machine classifier to do all sorts of interesting things. And that's the takeaway message. You can use just humans, that's fine, especially for folks with 100, 200, 300 responses. You still want to train them, and you still want them to do well. If you're in that category of researcher where you've got thousands of responses or tens of thousands of responses, or maybe you're sitting on 50 or 100,000 responses from a big employee survey or some customer survey, something like that, then some of these techniques for machine learning can be useful for cleaning up the data, or we do a lot of work around word sense disambiguation. Is it a money bank or a river bank they're talking about? Is it a Stanley Cup champion? Yes, hockey team, my team, or is it a flightless bird? Is it a governor with a bridge problem or a great writer? Is it the good kind of smoking or the bad kind of smoking, depending who you are? Is it your brand or one of 14 towns? with the same name as your brand, or a TV character with the same name as your brand, or a theater where Justin Bieber used to sit when he was a kid making his break into music. Basically, our deliverable is human coding into machine learning and trying to improve through crowdsourcing the way in which the timing, the speed, the accuracy, the effectiveness of all of that. So, thanks.
We have 5 minutes for questions. We have questions for Stu. Should have a microphone.
Hi.
Hi.
Hello, thanks for this. 2 questions. The first one is, what is your opinion about the Mechanical Turk as a way to do manual work? And I kind of...
It's cheaper than my coders.
And secondly, what do you do to a coder who delivers a 60% sort of result?
Fire them, or train them, but usually fire them. In my opinion of Mechanical Turk is it serves all sorts of researchers in very productive ways. Many computer scientists I know wouldn't dream of using the kind of team that we use. I use graduate students at universities in North America, South America, China, Europe. We have sort of multilingual teams assembled all over the place, sort of standing by and ready to go, but we pay them a lot more than Mechanical Turk pays, and then we also develop that relationship with them. It does turn out that some people are good at one task and bad at another. So that poor 2279, who I've been making a mockery of for years now on the stage, could be good at something else, but she was terrible at that. So, sorry, does that answer your question? Yeah.
Another question for Stu? Anyone? Over here.
Are you doing any image recognition with your
No, but Ditto.us is a great company that is, and we've talked to them a lot. They're neat people. Great technology out of MIT. I think it's Ditto.us. Ditto Imager. Yes.
Hi, I'm Lana, the founder of Heartbeat Technologies. You just made me feel amazing because I coded all my lexicon. So I hired a bunch of coders, trained them, and then when I got the data, sometimes it's good to be a control freak, sometimes it's not.
Yeah.
So I recoded the whole thing. It's 9,000 words and phrases about emotions. So, and what you're saying is actually, supported my thinking that I'd rather code it perfectly, well, as much as I can, perfectly first, and then go into machine learning, than to try to have machine learning fixing bad coding. So what's your opinion about it?
I'm all about the back and forth. Virtuous circle, use machines first where it makes sense, use humans first where it makes sense. So typically I'll deduplicate any data set I get, no matter what the source is, just to have a look at the landscape of duplicates and near duplicates, just to see what's in there. And then I can sample out of the duplicate groups or near duplicate. And so I'll use search terms to create customized subsets of the data so that I'm using purposive samples rather than just random samples. Sometimes I'll just take a random sample and I'll cut the coders loose and I'll say, what's going on in here? What are you seeing? And they'll do a kind of unstructured, inductive process and everything in between. Well, I've never thought that there's one right way to do this work. I've always used a variety of approaches, and it's usually contextually dependent.
Thank you.
Yeah.
Okay. Well, thank you, Stu.
Thanks.